Hi, my name is Carathian. I'm a member of the FreeFlyer technical support team, and I'm here today to talk with you about how to model BattleSpace contact timelines in FreeFlyer by reviewing the sensor-to-shooter sample mission plan. The sensor-to-shooter mission plan demonstrates the use of FreeFlyer to calculate the time required to uplink a location to be imaged to a constellation of 5 low Earth orbiting spacecraft from a command center, cross-link the location to all of the spacecraft, image the target location with the minimum acceptable elevation, and then download the imagery to a receiver on the USS Russell at another location on the Earth. This process to request and collect imagery for targets shows the high priority placed on shortening the information chain, or the sequence of steps taken to receive a command request for imaging, find and photograph the target, and then transmit the image to the fighter in the field. Now let's review the sensor-to-shooter sample mission plan code in FreeFlyer. To open the sample mission plan, we're going to click on the Browse Sample Mission Plans link on the FreeFlyer home screen. This will open a window that provides access to all the sample mission plan folders in FreeFlyer. This particular sample mission plan is going to be located in the Coverage and Contact Analysis folder. Once we open it, it will take us directly to our mission sequence where we can review the code. Now that we've opened the mission plan, let's take a look at the object browser and the objects available to us. We can see there's a number of different object types here, from an array for storing the spacecraft's attitude in the LVLH frame, to 3 ground stations, one to model our command center, one to model the target, and one to model the USS Russell. The next is a multitude of spacecraft, 5 of which are our low Earth orbiting constellations that will be performing the image analysis. When reviewing the spacecraft, we can see that all 5 have similar orbital elements, with only the true anomaly being the difference between all 5. This will allow our constellation to fly in a close formation while also providing ample opportunities for imaging collection. We then have 2 additional spacecraft, one that models our target and one that models the USS Russell. Now you'll notice when we open these GUIs that both have default orbits because we will define these via script. Next, we have a time span to represent the time when the command center requests an image, a variable to identify when an image was downlinked, and then a multitude of different vectors to help visualize the chain of imaging. Finally, we have 4 different view windows to show the constellation's orbit and location, as well as the sensor target view and the general target area. Now let's look at the freeforms themselves. The first is freeform number 2, the create objects. We can see in here, there's just a number of objects, mainly variables, that's going to be used throughout our mission plan. In freeform 3, we can see that we are initializing the colors for all 5 LEO satellites to be lime. This will help identifying when each of the satellites are either receiving a request for an image or actually taking the image itself. In freeform 4, we can see that we are configuring the visualizations for our mission plan. We can see in this first portion that all 4 of our view windows are using the set show body method to turn off the body for our spacecraft in LEO orbit, as well as the spacecraft representing our target and the USS Russell. In the next half of this freeform, we can see that we're setting the initial viewpoint for our target view camera, as well as the initial viewpoint for our sensor view window. Finally, we are building the cross-link vectors between our constellation of LEO satellites, and then we are building the comm vectors from our command center to our first spacecraft and from our last spacecraft in the constellation to the USS Russell. Next, in freeform 5, we initialize the values that will be used within our mission plan. We can see in this first portion that we are setting the ground site locations, where our command's latitude and longitude is located on the continent of Europe. our target's latitude and longitude is located within the country of Afghanistan, and the USS Russell latitude and longitude is located within the Arabian Sea. We can then see that we set the propagator step size for our initial spacecraft in the constellation and sync the remaining spacecraft step size to be the same. Finally, we set the request time flag to be 1 and the request time to be March 24, 2009 at 10 a.m. In Freeform 7, we're going to set the spacecraft at the target and USS Russell's location using the set fixed position method associated with the spacecraft object. This is done by using the ground station's fixed position, which is in the MJ2000 reference frame, to assign the location. Once the position has been updated, the Freeform then syncs the epochs of both targets using the epoch from the first spacecraft in our constellation. In Freeform 8, we can see some code to align the sensor with our target. In the first loop, we can see that we are using the initial spacecraft in our LEO constellation to determine if there's a contact or visibility with the target. If there is, then we will create a vector from our sensor to the target by assigning an epoch and then building the vector from the spacecraft sensor to the spacecraft target. Next, we'll then use the attitude convert method to go from our MJ2000 to LVLH reference frames, and once in the LVLH frame, we'll define the declination and right ascension. After doing that, we then want to point the sensor z-axis according to the declination and right ascension that was found in the previous steps. Once that's done, we'll then evaluate if there had ever been contact before or not, and if not, we'll then report that our first spacecraft is in view of the target. Once that's done, we'll activate our viewpoint for our sensor view to inform the user that is watching our output windows, and then continue on throughout the mission plan. If there is no contact during this initial loop, then we will just have the z-axis be pointed back to the ground. We can see that this code is being repeated for each spacecraft in our LEO constellation, where it is performing the same steps and process to determine if our target is in view of the spacecraft, and then if so, to update and notify the user. Next, in Freeform 9, we evaluate if the initial spacecraft's epoch is after the request time sent from the command center to the spacecraft. If it is, then the requested epoch will be updated with the current spacecraft's epoch, and then we will use another loop to determine the first spacecraft in contact with the command location and send a request to it. This is done by looking at our request flag and evaluating if our spacecraft are able to be in contact with the command ground station. If it is, then we will update our data array elements to identify that we have been in contact with command to receive the request, and then the epoch of the spacecraft contact with command. In the next freeform, once we've received our request for an image, we can see that we are taking an image of the target. This will happen when the first spacecraft in view of the target location is available to take an image. And we can see that this is done with a simple if loop to determine if we're in contact with the target and if we have already received contact with command to take an image. Once the image has been collected, we then use Freeform 11 to downlink the image to the USS Russell. This is done by using a series of if loops where we determine if the first spacecraft with an image is in view of the receiver on the USS Russell, and then downlinks the image. This is done with an if loop to determine contact and if the spacecraft has received a request and also taken an image. Once that has happened, we go through the loop and then we set the receiving flag to equal 1 so that it will terminate our while loop and exit because it has identified that we have downlinked the image. We can see that this loop and logic is repeated for each spacecraft in our LEO constellation. Now, in Freeform 12, we are transferring data between the spacecraft to inform the other spacecraft in the constellation of the current condition. This is done to authorize the remaining spacecraft in the constellation to capture an image of the target if they are the first to view it, or to let the remaining spacecraft know that an image has been collected and transmitted to the warfighter on the ground. While scrolling down the freeform, we can see that this logic is repeated in if loops for each time the first spacecraft comes into contact with another spacecraft. Finally, we reset the crosslink vectors for each chain in the constellation to allow us to complete our analysis. Then, in Freeform 13, we update the spacecraft colors dependent upon the data array element and if a request has been received or an image has been sent. And we can see that with all of these if loops in our freeform. Once the spacecraft colors have been updated, we need to then update the view windows in Freeform 14 to inform the user. We can see that at the beginning we're updating both the 2D and 3D view windows, and then we're splitting the windows to show a target and shooter once the command is received. Once we've updated the view windows in Freeform 14, the next portion of our mission plan is to step each of our LEO spacecraft so that their epochs sync with the first spacecraft in the constellation. After we step the LEO constellation, in Freeform 20 we then report if a command has been received by any of the individual spacecraft in the constellation. We're doing this via a series of if loops to determine if the command was received, yet no spacecraft had actually taken an image of the target yet. If a command has been received, then we will update the command received flag array to identify that throughout the remainder of the mission plan. Next, in Freeform 21, after the report command has been received, we evaluate if a report image has been taken. This is done using the data array elements to look and determine if an image was captured. If any one of the spacecraft in our constellation has captured an image, we will then report that the status of an image was taken at some set epoch, and then we will update the image taken flag array to identify that one was collected so as to complete the mission analysis. Next, once a report that an image has been taken, we need to report that an image was transmitted to the warfighter on the ground. This is done again using a series of if loops to identify if the data array elements have shown that the image was transmitted. If so, we will then report out that the image was transmitted at a specific epoch, and once that is done, we then go and update our image transmitted flag array to identify that it was completed and transmitted and received. Finally, the last freeform is used to report the time from request to receive. This is done by updating both our 2D and 3D view windows, and then calculating the report time from the received epoch minus the requested epoch, and report it out in minutes. Once that time has been found, it's then reported to an output file called request v receive delay, and we report it directly to a console to show the shortest delay of time between sending your request for an image and then actually receiving the image for the warfighter. This completes our review of the sensor-to-shooter sample mission plan to model BattleSpace contact timelines. If you found this useful, you can check out the rest of our how-to videos on our AI Solutions YouTube page. Otherwise, if you have any additional questions or issues, please feel free to reach out to our technical support team at any point in time. You can do this by contacting us through email at techsupport@ai-solutions.com or by calling us at 301-306-1756 extension 2.